As a paint sales and service professional, you're responsible for helping your customers successfully complete their painting projects. People paint for two simple reasons. First, they are interested in a clean, protective coating. And second, they are looking for a color to complement their design ideas. This program is designed to help you better understand paint color. Sounds simple, but as you'll see, pigments, colorants, chemical effects, the type of light, and the way you mix custom colors all have an effect on the outcome of your customer's paint job. The more you understand about paint and color, the better you'll be able to minimize mistakes and complaints and maximize profits and your customer's satisfaction. To understand how color works, let's begin by looking at three attributes of any color: hue, value, and chroma. Hue is the basic colors such as red, blue, or yellow. Value is how dark or light the color is. The lowest value color is black, and the highest value color is white. Chroma is the brightness or brilliance of a color. Regardless of their hue or value, low chroma colors are often called dull, dirty, or grayish. High chroma colors are often said to be bright, brilliant, pure, or saturated. Now let's look at how color works in paint. Color is added to paints and stains by adding a concentrated liquid called colorants. The preparation of colorants begins with pigments. All pigments are fine-grained powders with a consistent concentrated color. Pigments are processed intensively with additives, water, and other liquids to form universal colorants. These universal colorants are designed for use in water-based and solvent-based paints and stains that are manufactured to accept universal colorants. There are two types of pigment chemistry: organic and inorganic. Organic and inorganic pigments vary the paint's color in regards to its chroma, or brightness, its color permanence, and its opacity or hiding power. Organic pigments have a complex chemical structure, making it relatively expensive to produce them. The organic colorants are bright, high chroma shades of yellow, medium yellow or orange, red, magenta or violet, blue, and green. The simpler chemical structure of inorganic pigments makes them less expensive. Inorganic colorants include carbon black and the metal oxide pigments of red iron oxide, yellow iron oxide, brown iron oxide, white, and raw umber. For the most part, inorganic colorants are lower chroma, more dull colors. Another way to compare organic and inorganic pigments is their opacity or hiding power. This drawdown bar is loaded with paint tinted with an organic red colorant. The drawdown bar applies the paint sample in an even layer to the surface of the chart. The process is repeated with a paint tinted with an inorganic colorant, red iron oxide. Now compare this paint tinted with the organic red to the inorganic red iron oxide sample. The difference in hiding power or opacity is obvious. Another area of difference between organic and inorganic pigments is color permanence or light fastness. Light fastness is simply a measure of how quickly, if at all, colors fade over time from exposure to the sun's ultraviolet radiation. Colors that resist fading caused by ultraviolet light are said to have a higher degree of light fastness. Inorganic colorants, as well as the organic colorants of blue and green, have fairly uniform high levels of color permanence or light fastness. However, organic red, orange, and yellow colorants can contain a variety of pigments that in some cases may cause special concerns. The type of sun exposure and geographic location play major roles in the fading of paints. For instance, on surfaces located in the northern hemisphere, a southern exposure will allow more of the sun's ultraviolet rays to reach the surface, causing some paints to fade faster. The angle of exposure to the sun also affects light fastness. A vertical surface will be less affected than a horizontal or slanted one. In some cases, a breakdown of the coating itself gives rise to change in a color's appearance. When investigating visible change in a color's appearance, it is necessary to always check the condition of the coating as well. Altitude is also a factor, as higher altitude surfaces receive more intense UV radiation than those at lower elevations. Surrounding buildings, trees, and other sources of shade will reduce exposure to the sun's ultraviolet rays and thereby slow down UV degradation of the color. A particular symptom of this problem is differential fading. This occurs when one colorant in a formula fades faster than another, resulting in a shift in the hue from the original color, not just a lightening of the same hue. In this example, yellow and green colorants are blended to make a lime green color. With UV exposure and time, the yellow fades more than the green, so the color shifts in the bluer direction. This can be caused by differing levels of light fastness of pigments in a blend, or by certain combinations of organic and inorganic colorants. In pigments that are light sensitive, light colors fade faster than dark colors. For instance, a light pink will fade more than a deep red if the red pigment involved is light sensitive. The quality of a base paint being tinted can also affect the light fastness of a color. It's always a good idea to contact your paint supplier with questions about these and other characteristics of the specific colorants in their color system. Various chemicals can also have a negative effect on coatings and their pigmentation. Lime burn is a color fade problem that can occur when painting various substrates such as stucco, cement block, and precast concrete. Lime burn is affected by a number of factors. The longer the length of time the lime-containing substrate material has cured, the better the chance that the lime content has been reduced. The type or formulation of the substrate has a big effect. Cement-based materials vary widely in their pH. Humidity and sunlight, along with high pH substrate, are required to cause lime burn. The condition and preparation of the surface to be coated is key to ensuring that your coating performs as it should. The surface should be clean and dry, and primed with an alkali-resistant primer. The quality of and care with which a primer is applied can have huge effects on the lime burn of the top coat paint. Check with your paint supplier for primer recommendations. Remember, the longer the cement-based substrate has cured, and/or the better it is sealed with primer, the more the risk of lime burn is reduced. The best way to ensure against lime burn-related color problems is to avoid using colorants that contain organic pigments in the top coat. The safest colorants to use in coating any high pH substrate are the ones containing inorganic pigments: black, white, raw umber, red iron oxide, yellow iron oxide, or brown iron oxide. A 100% acrylic base paint is recommended. Strong oxidizing agents such as bleach, when applied to a surface as a cleaner, may have a harmful effect if care is not taken to thoroughly rinse any bleach residue from the surface to be coated. The same caution applies to cleaning the top coat of a previously painted surface. Magenta and blue are sensitive to oxidizing agents. Keep this in mind for jobs that may involve bleach for cleaning. Now, let's look at a commonly used arrangement of the various hues in a circle. This way of organizing color is known as the Munsell system. Colors located next to each other on the color wheel are called adjacent colors. Colors located across the color wheel from each other are known as complementary colors. Organic and inorganic colorants are used separately or in combination to create every color called for in a typical in-store color display system. When mixing custom colors, there are two factors to consider. First, there are several important differences between organic and inorganic pigments. Second, there is your choice of colorants to combine to create the correct color. It is important to consider the cost factor of inorganic and organic pigments when formulating colors. For cost-efficient color mixing, maximize the use of less expensive inorganic colorants and minimize the higher-cost organics. It's best to use only the minimum amount of organic colorant necessary to get the chroma of the color needed. For example, if you're blending the organic colorants of bright red and magenta, and your target color is a more dull, grayish or greenish looking, resist the temptation to add green colorant to the blend. This combination is guaranteed to have a higher cost and lower opacity than a color made with only two adjacent organic colorants and black or raw umber as the third colorant to impart the dullness needed. Using black or raw umber colorant instead of green results in greater opacity and lower cost. Let's take a harder look at cost. Here are two very similar samples of gray. One is formulated with organic red and green. The other made by mixing the inorganic colorants of black and white. It's hard to tell them apart, isn't it? The bookkeeper can tell the difference, though. The inorganic colorant in this quart of paint cost 18 cents to formulate, compared to $1.16 for the organic colorant. Two simple rules when formulating colors are: 1. If you find yourself in need of using more than two organic colorants, start over. And 2. When using two organic colorants, be sure they are next to each other in the hue circle. For example, blue and green, or red and magenta. There are several available strategies for matching paint or color samples which do not exactly match a sample included in your chip selection. First, let's look at manual methods done without a color computer. Never start from scratch. Starting with a sample listed in your formula book gives you a precise measurable point from which to develop your required color. Start by finding the chip in your color display system that is closest to matching your customer's sample. See if your customer is satisfied with that color. If they are not convinced that your color is an acceptable substitute, compare their sample to similar colors from your display. Find two colors that are fairly close to the sample but slightly off in opposite directions. Look up the formula for both colors and blend equal amounts of each formula into the base paint to get closer to the target color. Another way is to average the color by taking 2 times the quart formula for the sample on one side of your target color and 2 times the quart formula for the chip on the other side of your target color, and tint them together in a gallon of base paint. For that method to work, both of the chips you average must be colors made in the same base. If you can't locate a pair of chips from the same base that your target color is between, then try the following method. Go to the display rack and choose a chip that's as close as possible to the target color, but on the lighter value and higher chroma side, a lighter shade and more brilliant. This will provide a logical starting point. You will add colorant to modify this formula to bring the color match closer to the target color. As you add colorant to tune in your color, you will also darken the paint. It's much easier to start with a lighter shade, adding colorant to darken it, than trying to make a darker color lighter. If your target color is an intermediate red, pick a red with a slightly brighter, higher chroma and lighter, higher value. Add inorganic red iron oxide, or brown iron oxide, or maybe black to tone it down to match your target color. Remember, it pays to minimize the use of organic colorants. Computerized color matching uses an optical instrument called a spectrophotometer to analyze and determine a sample's color. This device aims a beam of light at the sample and measures the amount of light that is reflected across the visible spectrum of light. This information is used by the computer to calculate a formula calling for your colorants and base paints to match the sample. The specified formula is then printed out, often as a label for manual dispensing, or sent electronically to an automatic colorant dispenser. At this point, we've looked at paint and color in regards to organic versus inorganic pigments. We've discussed the effects of light fastness, opacity, chemical interaction, and different formulation theories. So now you're pretty sure you can match a color accurately. Well, there's one more thing you and your customers must consider before matching that color your customer wants. The appearance of any color changes based on the type or source of light that the color is being viewed under. Sometimes a pair of samples will match under one light source, but they will change differently when viewed in a second light. So the two will no longer match under the second light. This effect is known as metamerism. These gray samples are shown here under daylight, and here under incandescent light, and here under fluorescent light. If the color match between two samples changes as the light source changes, the match is said to be metameric or conditional. If two samples continue to exhibit a good color match when illumination changes, the match is non-metameric or unconditional. It's important to understand the cause of metameric color matches. Usually, it is different pigmentation in the two samples. This can arise in two ways. 1. Different pigments or different colorants in the case of custom mixed paints are blended to arrive at the color match. An example of this is the gray pair of samples we saw a moment ago. The target color is made with white and black pigments, and the matching sample is made with white, red, and green. The color match between these two paints will be very metameric or conditional. 2. Differing pigmentation is often unavoidable when dealing with differing types of colored items, such as paint versus ceramics, fabrics, plastics, inks, etc. Therefore, metameric color matches are very common when comparing paint to a non-paint target color. Another type of metamerism, very important to us in the paint business, deals with color matches that are conditional on the angle or the geometry of viewing. For example, there is a perceived difference in the appearance of a given color formula when it is mixed into base paints of differing gloss levels. The explanation is related to how a mirror works, by reflecting light at the same angle as the light striking it. Light reflected this way is called specular reflection. Specular reflection occurs when the surface being illuminated is highly glossy, for instance, a mirror or a high-gloss paint. As that gloss drops, more of the light that is reflected goes off at diffuse angles, and less is reflected at the specular angle. So when comparing two samples of differing gloss or sheen, the angles at which the samples are illuminated and viewed can be critical. In most cases, holding the samples in a way that eliminates the specular reflection from view is the most meaningful way to compare the colors. If, on the other hand, the specular reflection is included in what you see, it will make the glossier sample appear to be lighter. These gray samples, shown here under laboratory daylight, were created using the same formula in base paints of differing gloss, flat on the left and high gloss on the right. The color match is close when the samples are held and viewed in a way that excludes the specular reflection from view. But when the angle is changed to the mirror or specular angle, the additional reflection from the high gloss sample lightens its appearance considerably. Same colorant formula, different gloss of the base paints. As you've just seen, the type of light, the gloss level, and the comparison of paint versus non-paint samples can all affect the actual look of the desired color. It's important to ask your customer a question or two about what and where they are painting. Find out what type or types of light will be illuminating their painting project. If the customer gives you an object to color match their paint to, try to view the match under the right type of light. Finally, it's important to remind your customers that colors will often appear darker when applied to a large area. Your color match may be perfect to the color chip or your customer's sample, yet appear much darker when covering an entire wall or room. With the proper use of colorants, you can satisfy your customer and your bottom line. When mixing paint, remember that inorganic colorants such as red iron oxide, yellow iron oxide, brown iron oxide, white, and raw umber are less expensive, have greater opacity, and have a higher degree of light fastness. Organic colorants, such as the brighter shades of yellow, orange, red, magenta, violet, blue, and green, are more costly. They have a lower opacity, and in some cases, a lower degree of light fastness. Remember to try to use inorganic colorants when you are mixing paints. Color will appear different depending on the type, condition, and location of the surface. Lighting conditions and even the size of the area to be covered will affect the color, so it's a good idea to discuss the painting project with your customer. And remember to refer to the container labeling when explaining product attributes or answering your customer's questions. When you take an interest in your customer's project, you're building the success of your business. Success means happy, satisfied customers that you can expect to see the next time they need a helpful and knowledgeable paint professional.